Okay, today we're going to talk about Markov decision processes, which are a generalization of search problems where you're not entirely sure what your actions are going to do until you try them. So why would we consider a kind of non-deterministic search, right? We had our search problems before. They had states, they had actions, they had costs, and we made plans. We perhaps be moving a robot around a grid to accomplish some task, or a Pac-Man around a board. The reason why we need to have a non-deterministic search is because in the real world, often you know what actions are available to you, and you know what they might do, but you're not entirely sure what outcome will occur. So for example, if you're this robot here trying to cross this ledge, you know you can shimmy to the side and try to get that gem, and it might work, or you might fall into the pit. And so when you take an action, you may know the possible outcomes, but you don't know which one is going to happen. And so you have to make plans, or more generally, compute policies that take into account all of the different outcomes that might occur in response to your actions. One example of not knowing what's going to happen is when you hit the space bar. Usually you get the next slide. But sometimes it all freezes up. Luckily, my policy knows what to do when that happens. So we're going to have a couple running examples. Just like when we talked about search, we had running examples of search. So we talked about the specific examples of search, or CSPs, or games, and then we talked about the whole class of search problems, or CSPs, or games. The running example we're going to use for MDPs, Markov decision processes, is grid world. But just like in all those other cases, it's just a running example. So in grid world, we have a maze, we have a robot, we have north, south, east, and west, and we're going to have a bunch of grid world concepts, which are really good for illustrating the kinds of things that happen in MDPs. But we're going to have to be really careful that we don't overfit. It's a flash forward to the machine learning section at the end. We don't want to overfit to this particular example. So in grid world, which is just one of a whole rich world of possible MDPs, we have a problem that looks a little bit like a maze. The agent is going to be on a grid, and there are going to be walls blocking the agent's path. I love it when they install stuff for me. Let's go. Get rid of you. Okay. There are going to be walls blocking the agent's path. This is a lot like moving Pac-Man around a maze, except now there's going to be some non-determinism. And in this case, in this particular MDP, that non-determinism is going to take the shape of noise. So in this grid world, say 80% of the time, when you take an action, which might be called north, you'll actually move to the north. Remember, in search, you would just decide where you want to go, and then you'd be there. But here, you try to move north, but it might fail. So in grid world, your actions might succeed, and that means you're going to move in the direction you attempted to move. Or they might fail, which means something else happens. And in this formulation of grid world, and we could formulate grid world a million different ways, formulating a problem so that it matches the real world problem you're trying to solve is one of the challenges in using these techniques. But in this grid world, 80% of the time you go where you expected. If there's no wall there, if there's a wall there, you'll just bounce off and stay put. The other 20% of the time, you either go counterclockwise or clockwise a direction. So 10% of the time, if you try to go north, you'll actually go west. 10% of the time, if you try to go north, you'll actually go east. In this grid world, you're totally safe from going south. That's something that will never happen in this model if you try to go north. Is this how the real robots work? Not really. This is how the grid world we're going to use for this lecture and the next one works. If there's a wall in the direction you would have gone, you stay put. All right. That's sort of the rules about where you can move. You can move north, south, east, west, but it might fail, sending you in an unexpected direction. Now let's talk about the equivalent of costs from search. In MDPs, the costs are called rewards, and here we receive two kinds of rewards. There's sort of the primary grid world reward, which is that you exit the game, and there's kind of good exits and bad exits, and they're labeled with a value. So in this case, the gem might be the good exit. If you can get to that square, you take the action exit, it ends the game, you get your +1 reward, and you're a happy robot. If you fall into the pit, you also take the action exit. You receive your -1 reward. The game still ends, except now you're a sad robot. Those are the big rewards. They can be good or bad, positive or negative. And in Grid World, to illustrate some concepts, we sometimes also have a living reward, which happens every step that you don't exit the game. So for example, in this position here, I might decide to take the action north. Maybe it succeeds and I actually move to the square to the north of the current robot, and I get a little reward. It could be a tiny little boost, a positive reward, or it could be a tiny little bit of pain or something like that as a negative reward, or it could be big, or it could be 0. That's something we can change, and that's something that you get every step of the game. This notion of a living reward and a big reward at the end and a gem and a fire pit, these are all Grid World concepts. But the idea that when you take a transition from a state to another state, you receive a reward of some kind, that's an MDP notion. The goal, loosely, because we're going to revisit this later in this lecture, the goal loosely is to maximize the sum of the rewards. Okay, so you would like to take action so that you get the gem, but you don't fall into the pit. Okay, that's a lot like search, right? When we were trying to take actions which, in that case, minimize cost, now we're trying to maximize rewards. In a deterministic grid world, we could have solved the problem with search. We could have said, all right, I'm in this state here. And what can I do? Well, I can move north, I can move west. North is a good move, west is a bad move, so I'll move north. And when I choose that action, I know what's going to happen. There is one outcome per action. That's what it means to say you have a deterministic search problem. In a Markov decision problem, it's non-deterministic, which means when I'm in a certain state, like the robot's right there to the right of the pit, and I choose to move north, there's multiple things that could happen. Okay? Importantly, in an MDP, I know the set of possible outcomes. And it's actually going to turn out I know the probability that each one will occur. I just don't know which one will occur in a given run. So when I plan to go north here, I know I might go north, or I might go to the east and have to replan from there, or I might go to the west and fall into the pit, and that'll be bad. And as I plan, I need to take these things into account. So I might take, for example, a cautious sort of behavior that takes into account all of the possible failures along the way. So in general, an MDP, a Markov decision process, will be defined much in the way a search problem was by a set of quantities that define the problem. There's a set of states. This is very much like in search. These are the set of configurations of your problem. There's a set of actions. And we had these in search too. Sometimes we didn't really talk about the actions having labels when we talked about, say, depth first search. But there were neighbors. There was a successor function. And in your code in Project 1, you did actually have to manage the labels of the actions. So this is something that's been there all along. There are states and there are actions. The difference is that in search, when you're in a state and you take an action, there is a successor state and a cost. In an MDP, there's not just one successor state, there are multiple. So we've got our states like before, we've got our actions like before. But now, if I'm in state S and I choose action A, there may be multiple states S prime that can occur as a result. And so what I will have is what's called a transition function, which describes from state S and action A what S primes can happen and with what probability. So people write TSAS prime and call it a transition function. But what you should have in your head is this is for being in state S, choosing action A, and what I care about is the probability that every possible outcome S prime happens. So TSAS prime is in this sense a conditional probability that S prime will happen if you were in state S and chose action A. Another important quantity in an MDP is a reward function. So a reward function in general is going to be a positive or negative or 0 reward that you get if you're in state S, you choose action A, and you land in state S prime. Sometimes it'll only depend on S, sometimes it'll only depend on S prime, sometimes it'll depend on the entire triple. That triple is often called a transition, and in general we'll write the reward function as being a function of where you started, what you did, and where you landed. So if you're standing next to if you're on the cliff trying to cross the cliff, there might be one reward for making it across and an entirely different reward if you fall into the fire pit. In general, there's maybe a start state. There might be a terminal state. This is where things start to differ. In search, there was this really important notion of a goal test. These are the states where we stop. We've achieved our goal. In MDPs, in full generality, the game sort of just keeps playing. And sometimes you get into a state where it stops. Sometimes the games go on forever, and we'll need to be very careful with our algorithms and our formulations that we understand what that means that a game may go on forever. So MDPs, like I said, are a class of non-deterministic search problems, and they will require a new class of algorithms to solve them. So A-star search won't do it. That's for deterministic search problems. So how are we going to solve MDPs? We're going to talk about a bunch of algorithms today and next class. And then, in some sense, the week after that as well, because it turns out that MDPs are the foundation for reinforcement learning as well. However, you actually already have an algorithm for solving MDPs. It's called Expectimax search. When you learned about Expectimax search, it might have felt like a weird variant of Minimax, where the opponent was rolling dice or something like that. But it's actually the more general algorithm, and here we'll see that it's very tightly related to the algorithms we use to solve MDPs. Okay, so MDPs are like search problems, but instead of knowing what your action will do, you have a distribution over possible outcomes represented by the transition function. Okay? Any questions? All right. So who's this Markov guy, and what's he doing in my decision problem? Markov in AI usually means something about the present state, and it means that given the present state, the future and the past are independent in an appropriate sense. And in a Markov decision process, what Markov means is that the action outcomes, so those transition probabilities of what will happen if I take this action in this state, they can depend on the state, and they can depend on the action, but they can't depend on the past. So if I want to know, I'm the robot, and I want to know what's going to happen if I try to cross this bridge, well, it depends on where I am and what I'm doing, but it doesn't depend on the route that I took to get there. So if you'll remember, this is just like what we had in search. We had to be very careful to formulate our search problem so that the state had any information stuffed into it that was necessary to let the successor function fully describe the problem. And so with search, we often formulated, all right, okay, my state can't just be Pac-Man's position. It's also got to be which dots I've eaten, or where the walls still are, or whatever is appropriate for that variation. MDPs are the same way. We often have to be careful how we formulate our states so that they give us this Markov property, that if I know the state and I know the action, I can tell you the distribution over what happens next in a way that's independent of what's happened in the past. Okay. Thank you, Markov. Here's another big difference from search. In search, we had this model of the agent that looked at the search problem and did a bunch of offline computation, thought, and came up with a plan. What's a plan? A plan is a sequence of actions. And then we would execute that plan step by step. And as we executed that plan, our master design would fall into place action by action, and we'd end up at the goal state exactly the way we planned. MDPs are for a noisier world. And so we can't really have a plan, because it might work or it might not. So let me give you an example. I'm going to pull up Grid World here. All right. Here is Grid World on the right. And here on the left, you're going to see, you can't really tell what I'm pressing, so you'll be able to see what happens for each transition as I press. So here the robot is the blue dot. And you can see 1, that's the good exit with the gem. -1 is the bad exit with the fire pit. And I'm going to press north, south, east, or west, and the robot may or may not go the direction I press. So what direction should we go? Let's try north. I'm going to press the up key on my keyboard. What will happen? Who knows? Okay, so it worked. All that suspense. This said, started in state 0, 0, took action north, ended in state 0, 1. That is a transition. S was 0, 0, A was north, S prime was 0, 1. And I got a little reward. My reward was -0.1. In this particular configuration of Grid World, you get a -0.1 each time. And that might affect your behavior. So as we change the living reward up and down, we'll get different grid worlds in which the optimal actions are going to be different behaviors. We'll see that in a second. So I'm going to try to go north again. I'm going to press north again. Okay, it worked. So far it's acting pretty deterministic. So we started in state 0, 1, we took action north, and we ended in state 0, 2. We might not have. We might have ended somewhere else, but that's what happened this time. That's a transition, S, A, S prime, and we got an instantaneous reward minus 0.1. So far, my rewards are minus 0.2. Okay, I'm going to try to go east. It worked. Do something random. Okay, I went east and it worked. I'm going to try to go east again. Oh, look at this. Started in state 1, 2. I took action in east, and I ended in state 1, 2. That wasn't the most likely outcome, but that's what happened here. And so when I plan, I need to plan knowing that these things might not go the way I expected. So if I had just blindly executed up, up, east, 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 exit, I'd be in trouble because something didn't go sort of according to plan. Something didn't have its most likely outcome here. I'm going to go east again, though, because that's still a good idea. Whenever I'm in that state, that's a good idea. Okay, now I'm going to go east again. Now here it starts to get a little bit suspenseful, because I could successfully go into the good exit, or I could move perilously close to the fire pit. Let's try it east. Lucky. Okay. And then from this point, you'll notice I received only that living reward minus 0.1. I didn't receive the plus 1. That doesn't happen until I take the action exit from the square. And you think, who cares about exactly when it happened? Well, we're going to use this running example enough, and it's going to be in your project, that it's good to know exactly when it happens so you don't have off by 1 errors all the time. All right, so here I go. I'm going to exit. Boom. And what happened here? Let's scroll up. I was in state 3, 2. I took the action exit. I ended in the special state terminal state, and I got reward 1. So my total cumulative reward was like 0.7 or something like that. I'm going to do it again. All right. Let's make this a little more tense. I'm going the scary way. I'm going to go east. East. I'm going to go north. I'm going to walk past the pit. North. All right, I'm going north. Anything could happen. Okay. All right. Some years this is really intense, but not this year. All right, so you get the idea. But even though nothing spectacular happened like falling into a fire pit, you did see a couple times where I expected the most likely outcome would be I'd move east, but I stayed put. Okay, as a result, we can't have a plan, which is a sequence of actions, because who knows what's going to happen when I take those actions. For MDPs, the analogous concept to a plan is something called a policy. A policy isn't a sequence of actions you take. It is a function which in a state tells you an action. So it's like a recommendation of an action function. Okay, policy, you give it a state, it gives you an action back. In general, when we say we solve an MDP, we're not just interested in any policy, we're interested in the optimal policy. The optimal policies are pi, that little star throughout these lectures, and in general in this class is going to indicate optimality. So we want pi star, which is an optimal policy. There may be multiple equivalent policies. Okay, a policy gives an action for each state. An optimal policy is one that maximizes the expected utility if followed. And an explicit policy is an actual explicit enumeration for each state of where you should go. And so, for example, this map here that the robot's looking at for the grid world, that is an explicit policy. It lists each state and what to do. That means following this policy is a reflex agent. You look up your state, you look up the action, you do it. No computation is required. All the computation went into building this policy in the first place. Once you've got it, you just do it. Sometimes that's realistic, sometimes it's not. So for example, in something like Pac-Man with dots, the state space may be so large you could never compute or even write down the explicit policy, and so we would need different methods. What we're going to talk about today assumes that the MDP is small enough, the state space is small enough, that we can actually enumerate the states and write down policies. That's not always going to be true. If you remember Expectimax, that didn't actually compute policies either. You just executed it as a computation in a state. It churned on the game tree for a while, and then it said, take this action. So Expectimax might be living inside a function pi that computes the policy on the fly, on demand. That's not what we're going to talk about today, but that is another class of ways you can build policies. Instead of being explicit policies, you could have an implicit policy that requires computation each time you try to access it. All right, let's take a look at some optimal policies. So you can see the optimal policy right here. So there's the gem. there's the fire pit, and there's this policy that says, all right, if you're here at the start state, you should go up and around and into the gem. Okay, fair enough. What gets more interesting is in some of the other squares. So for example, if you're in this square here, this policy says that you should take the short way, right? You should take the short way around and risk the pit. Why? Why don't you go the long way around? Well, this is going to be a function of exactly how the living reward, which here is a penalty, balances against the risk you take by walking past that pit. And this is a general example of we feed in the specification of the model, and the behavior emerges through the computation. Okay? So let's look at some examples of different kinds of behaviors all emerging from the same computation of solving an MDP to get an explicit policy for grid world. So here's an example. There's still a +1 and a -1, a good exit and bad exit. And remember, each time step that you don't exit, you get a little reward. In this case, it's negative. So you get hit with a tiny little tax, -0.1, each time step. I guess it's more of a toll than a tax. And if you look at this, you can see that, as you'd expect, if you're at the start state, you might as well go the safe way. But if you're here, even though you're quite close to the shortcut, it's still going to send you around the long way. And that's because that living reward is so minor that it's not worth the risk of falling into the pit, which is a significant risk. So you just pay the extra price to go around. You might slip a little bit as you go. It might take a little longer, but you basically go around the long way. Here's the really interesting square, right here. What the heck is that? The living reward is very small, and that means this agent has a lot of patience, right? It can afford to take a lot of steps to get a large reward later. So it's doing this odd thing where it's moving into the wall. What's up with that? So we fed all the rules into the agent, and what did it do? It solved it, and it basically learned an exploit. Grid world has a bug, and this agent learned it. What is the bug? If from this grid square here, if you go north, you might fall into the pit. If you go south, you might fall into the pit. If you go into the pit, you're probably going to fall into the pit. But if you head towards the wall, there's no chance of falling into the pit. What's probably going to happen? Nothing is probably going to happen. You're probably going to end up where you are. But if you do it enough, over and over and over again, eventually you'll sort of slip to the left or the right, and you will have escaped the danger square without any risk of falling into the pit. Okay, so this is, if you remember back, you remember the little Ibos playing soccer, where the way they shoot is they put their stomach on the ball and then poop it out? Okay, this is more or less a spontaneous discovery of a behavior which is optimal but maybe not what you would have predicted, and it's a consequence of the rules of the game. All right, we can turn up the temperature here and charge the agent more per step so that taking your time is no longer going to be as appealing. And so in this case, you still, go straight, you prefer the good goal to the bad goal. But here you're gonna risk falling in rather than taking 10 turns to shimmy your way out. But you'll still go the long way around if you're in one of these squares. Let's turn up the heat again. Here the reward is -0.4. Think about that. It's starting to be almost as big as the rewards at the end of the game. So now, this agent is not going to mess around. Given the choice, it would rather take the safe way than the dangerous way. But if you're in this square, you're just going to run for it. Maybe you'll fall into the pit, but that's okay. Because if you go the long way around, you're going to accumulate so much negative living reward that doesn't make sense. What do you think is going to happen if I crank it all the way to -2? Think about that for a second. That fire pit starts to look pretty good. Because it's better than the reward you get every step. And so what are you going to do? Straight to the closest exit. Get me out of this game. Okay? All of these different kinds of qualitative behaviors will emerge from the same kind of computation, just as the differences in rewards and the balances of those shift. Any questions on that? Okay, now we're going to see how to compute this stuff. That's grid world. It's really, really easy to think of search problems as happening on a grid, and by now you know that many search problems have nothing to do with a grid or any kind of spatial structure. I'm going to give you another example of an MDP that looks nothing like grid world. to give you a second running example that we're going to work a lot with today and next time. So this is a super, super simple example of a robot car. It's a very, very simple example that has only 3 states. And what you see here is a state transition diagram, think like a finite automaton, that describes the states and how they interact in this MDP. So we have a robot car. It would like to travel far and quickly. And it's going to have 3 states, obviously a huge simplification. There's going to be cool, warm, and overheated. And cool is the good state. The car would like to be cool. Warm is okay, but you start to risk overheating, and if you overheat, the game's over. It's not actually directly good or bad to be cool, warm, or overheated, because the rewards happen on the transitions. And in this case, you've got actions slow and fast, and the way the rewards happens on the transitions is that you get twice as many points for moving fast than for moving slow, regardless of where you land. The rewards can depend on where you land, like they did in Grid World. Here they don't. They only depend, in this case, actually, on what state you're in and what action you take. So let's look and see if we can just sort of wrap our heads around this example. So if you are cool, if the car is cool, and you choose slow, you will get your +1 reward because you went slow. And with probability 1, you'll stay cool. All right. What happens if you go fast? Well, if your car is cool and you go fast, you get the +2 for going fast. But what happens next is not deterministic. Half the time you stay cool and half the time you warm up. If you're warm and you go slow, you get the +1 reward for slow. Half the time you stay warm, but half the time you cool down. If you're warm and you go fast, you get a -10 and you overheat. And if you overheat, the game's over. So what should you do? What should you do if it's cool? Go fast. What should you do if it's warm? Don't go fast. Yeah, go slow. And if you're overheated, you should reflect back on the decisions that got you there. In this case, you do not have to end up there ever. So there you go. This is a little MDP. It's got a very small number of states, but you can imagine the games can get very long because there's no real end to this game unless you make a mistake. Okay, that's an example of another MDP. All right. So let's think, if we wanted to figure out, it's cool. I just asked you. So if I want to know what to do when the car is cool, apparently you can just ask CS188. But if I wanted to do that computationally, how would I figure out what the right action is? You've sort of already got a tool. You've got Expectimax search. But I can think, all right, if I want to decide what to do from the state cool, I can think out the possible futures, just like we did with games last week. Okay, and if I think out the possible futures, I'll think, well, I can go fast or I can go slow. That's going to be under my control, but both are possible. And if I go slow, only one outcome can happen from my taking that action, and that is I end up back in the state I started in. If I go fast, there are 2 outcomes to that action. I'll either stay cool or I'll heat up. I don't know which will happen, but I know they both can happen, and I know the probabilities associated with them. Now you might wonder, what if I don't know the probabilities? I would say come back next week for reinforcement learning, where we'll learn the probabilities. For now, we know about them. Okay? And then I can just kind of keep extending this into the future, and I can see this tree which will look exactly like an Expectimax tree. There will be an alternation between actions that I can choose amongst, and then chance nodes which describe the possible outcomes, which I know a distribution over, but I can't force an outcome. It's not going to be as bad as worst case, there's just a distribution. Okay, so here's a search tree that describes that. One thing should already strike you about this search tree. Anybody notice anything that didn't really happen in Expectimax? One thing is it's the same 3 states over and over and over and over again. So doing some exponential amount of computation over these 3 states just can't be the right thing, right? Because these same subtrees appear. This tree here is exactly the same as this one here. So we're going to want to be careful of that. In general, whenever you have a Markov decision problem, you can think about there being a tree like this projected from each state. So from each state, there is a tree of futures that has that state at the root, and then the actions available to you branching out. When we talk about S is a state. Okay? The actions are A. Those are the actions available to you. And we've had those for a while. Now here's where we get to something that's new and a little bit counterintuitive, but super useful. What are these chance nodes from Expectimax? What do they represent? Well, S is a state of the world, and A is an action you choose. And then after you choose an action, it's going to resolve to some state S prime, and there's going to be multiple possible outcomes which are governed by a probability distribution. But what about this node right here? I was in a state. There could have been other states. I was in that state. I chose an action. It may or may not have been a smart action, but I've chosen it. But I don't yet know what happened as a result. Being in this situation where you're in a state and you've committed to an action, but it has not resolved, is called a Q state. Okay? And it represents having chosen an action but not seen its resolution. This whole sequence here, this little tree, SAS prime is called a transition. And on this arc right here, when your Q state SA resolves to a particular result S prime, that's a transition. It's labeled with a probability from your MDP as well as a reward. And here that reward is shown as a gem, but the reward can be negative. For example, both the fire pit and the cliff, both the fire pit and the living reward were both negative. Okay? So this little search tree, this is MDPs in a slide, is the search tree. Everything we do, every algorithm, every quantity, it all comes back to this search tree, where you have a state, a sequence of actions that you maximize over, and for each action, a sequence of outcomes which you have a probability distribution over. Okay? We'll talk about solution in a bit. But let's take a step back and try to figure out how an agent should think about a sequence of utilities. Because another thing that happens in an MDP is that you saw when we were in grid world, those rewards would sort of be trickled in step by step. So we need to be able to think about our preferences over these sequences. So what preferences should an agent have over a sequence of rewards? First, should an agent like more rewards or less rewards? So for example, if I give an agent a choice between a sequence of 3 rewards, 1, 2, and 2, or 3 rewards, 2, 3, and 4, which one should it pick? Well, I guess I have to define whether positive is good or not. In this case, we've been talking about them as rewards, so it seems pretty reasonable that the agent should prefer to get more rewards rather than less. Okay, great. If that's all I wanted to accomplish, I would just add up the rewards and I would say, hey, agent, go act in such a way as to maximize the sum of rewards. But there's one other thing that turns out to be really important in MDPs, and that has to do with a choice between now or later. So for example, here's 2 sequences of rewards. One is 0 rewards, followed by 0 reward, followed by a reward of 1. Or another sequence where it's a reward of 1, followed by 0, followed by 0. Same sum of rewards. What should the agent prefer? The reward now or the reward later? Or should it be indifferent? How many people say reward now? Give me your rewards. How many people want the reward later? How many people are indifferent? Okay. So it is totally reasonable to be indifferent, right? Sometimes that's an appropriate formulation. But in most cases, and most people raise their hand for rewards now, in most cases it is also reasonable to prefer rewards sooner. Okay? And so how are we going to handle that? Adding up the rewards doesn't actually capture the fact that rewards soon are more useful than rewards later. For example, if somebody comes up to you and says, hey, would you like $100 now or in 20 years? Will you be indifferent? What if they say, and of course, that's totally, it's easy to see that you might say, well, I'd rather that reward now. But what if they say, would you like $100 now or $110 in 20 years? You probably still want the reward now. And so that means there's going to be an implicit trade-off between having things soon and having things be big. So, it's reasonable to maximize the sum of your rewards. In fact, that's what we've been doing so far with Grid World. It's also reasonable to prefer rewards now to rewards later. One solution to capturing these different reasonable utility functions is to say that the values of rewards are going to decay in an exponential way. So for example, here's a reward, and if you get it now, it might actually be worth 1 right now. But if you think about that reward, that same reward being in the future, it could be worth the same, then you would just be summing rewards, or we can penalize it. A way that's very convenient formally and mathematically to penalize things is to say that in the next time step it won't be worth 1 anymore. It'll be worth less. It will be discounted. It will be worth some amount gamma, which we can pick. Gamma has to be greater than 0 to make sense, and it has to be less than or equal to 1. if you want the things to be worth less later. But there are different points you could set in between. And then in 2 time steps, it would be worth gamma squared. And so the value of a reward will decay exponentially, where the rate of that decay is something that is actually an input to the problem rather than something you can derive. Okay? So 2 questions. One is, how do we discount? And the second is, why do we discount? So how we discount is actually the easier of those questions. So remember, if we think about there being this tree of possible futures where every time you take an action, sort of the world responds with telling you how that action, what the outcome was. So here you were at S, you took action A, you landed in S prime, and at that point, there's this little call out which is, hey, I was at S, I took action A, I landed in S prime. So here you go, you can have your reward R of SAS prime. And then you get another reward here. You get another reward, and another reward here. And what you can do is conceptually you want each of those rewards to get hit with an extra factor of gamma, and say if you were running an Expectimax search, you could just set it up so that each time you recurse to the next level of the tree and you return a result, you hit it with a factor of gamma, so that each level down picks up an extra factor of gamma. This has some really interesting properties, like things way, way in the future eventually just don't matter very much because they've been hit with so many factors of gamma that they're just not worth very much to your computation. So why should we discount? One is that sooner rewards probably really do have higher utility than later rewards. And sometimes this sort of like has to do with the mechanics of the problem itself. Like maybe this is money and you can invest it or something like that. And there is actually a story where the mechanism is something exponential or something decaying in value. But it also helps our algorithms converge. And there's another reason why these are very convenient, which I'll talk about in a second. Okay? So that's discounting. In general, in MDPs, we say either we sum the rewards or we sum them up with a discount that hits each time step so that things farther out into the future are worth exponentially less. And if you think about it, these are actually the exact same thing because if you set gamma equal to 1, you'll end up with the undiscounted case. Okay, so if you think about a discount of 0.5, that sequence 1, 2, 3 is not worth 1 plus 2 plus 3. So 1, 2, and 3 are the rewards. The utility of the sequence could be the sum of the rewards, or it could be the sum of the discounted rewards, which is in general what we'll do. And here that means it's 1 times 1, because it hasn't discounted yet, plus 2 at the second time step, but it gets hit with a discount, in this case 0.5. And then on the third time step, you get a 3, but it's been hit with that discount twice, so it's only worth a quarter of what it would have been worth at the current time step. And so the sum here isn't 6, it's much less. And that 3, even though it's the largest number, is actually worth less than the 1 at the next time step. Okay. So if you look at this, among other things, this means that 1, 2, 3 is not as good in utility as 3, 2, 1. So when we specify an MDP, we have to specify a discount which tells us how to turn the sequence of rewards into a utility over the sequence. It's either going to be the sum or the discounted sum. All right. Remember when we talked about utilities, and we talked about there being even before you have utilities, which is going around and assigning numbers to outcomes, we talked about something more primitive, which is preferences. I like 2 scoops of ice cream more than 1 scoop of ice cream. And then I can go around saying how many utiles each scoop is or something like that. We talked about there being a set of rational preferences. These are preferences that seemed like any reasonable set of utilities should respect them. And then we could derive things like if your preferences obey these rational constraints, then they can be formulated in a certain way as a utility function. There's an equivalent notion here for sequences, and it's a notion of stationary preferences. So there's a theorem that says, let's imagine that your preferences are stationary. That means if you prefer the sequence of rewards A1, A2, A3, A4, and so on, to this other sequence B, B1, B2, B3. So you like the A sequence better than the B sequence. Great. Who cares why? You like A better than B. If I tell you, hey, how about for the first time step, I'll give you the same reward R, and then I'm going to give you A and B. Well, if you liked A better than B now, and your preferences are stationary, it means you will also like A better than B shifted 1 time step if that first time step has the same reward. it seems like it's reasonable to assume that preferences are stationary. If preferences are stationary, it turns out there are only two ways to define utilities, which, as we talked about, are basically the same thing, which is you either sum the instantaneous rewards at each time step, or you sum them with a discount. And you think, that's a little weird. Maybe my preferences aren't stationary, and sometimes they're not. Because, for example, if you are playing a game like, say, Life, where you don't have an infinite number of time steps, it could be that by pushing the rewards out, something just comes too late, something falls off the edge or something like that. And so when things have finite horizons, sometimes things get trickier and have to be handled in different ways. All right, let's do a quick quiz. First, any questions before we quiz? The quiz is gone. Any questions? Yep. It's a great question. The question is, why are we doing exponential rather than subtractive discounts? So let me separate two things. Very important. There's two things going on in a grid world, not an MDP in general. A grid world, robots, north, south, east, west, and so on. There is a living reward, which might be a penalty at each time. That is an R. That's a reward. That has nothing to do with a discount. Then there's a discount, which so far we've been talking about the grid worlds as having a discount of a 1. They were undiscounted so far. So you can always penalize at each time step as part of the reward structure. But mathematically, when you talk about sequences being converted into a single number, that's when we use the exponential formulation. And the reason we do that is, one, it's mathematically very convenient. It helps us prove that things converge. It reflects a lot of real-world things. In many cases, by pushing something out in time, for example, interest and so on money, things really are exponential. And then beyond that, there's also this theorem about stationary preferences, which only holds for the exponential case and not for the additive case. But it's a great question, and sometimes we do actually, like in grid world, want to have something additive going on where every time step costs the same. And we can do that too. Okay. Yep. I'm sorry, could you ask it again?
It's a sequence of the reward. So how can I know the sequence if the future is undetermined?
So the question is, how can I know the sequence of rewards when the future is undetermined? And before you act, you don't know what sequence of rewards you will get. But what these algorithms do is they plan, I could take this action, I could take that action. And based on the actions I take and the actions I might then take later, I have to sort of hedge with all of those possible outcomes and probabilities in the appropriate way. So we need to be able to compute, okay, if I had this reward or I had this reward, how would I combine them and how would I think about them? But it's true, you don't actually know which future you're going to get until you actually play the game. So solving an MDP happens offline. You don't actually play it. You consider the probabilities and you make your policy. You can then go actually execute the policy. And then you're going to get one particular experience. And that's going to be analogous to what we do in reinforcement learning, where we just play the game and something happens. And the next time we play it, something else might happen. And then we'll be in a position of having to learn. Right now, we know the rules of the game. And so even without actually playing it, we can solve in a way that hedges all of those various probabilities appropriately. Okay, great questions. Okay, let's do a quiz. Quiz on discounting. So this is a grid world. You can go east-west and exit. You can only exit at A and E. It's deterministic, so that if you go east, you'll actually go east. And if you exit at A, you get 10. If you exit at E, you get 1. If gamma is 1, what is the optimal policy? So what should I do, say, at B here? I should go this way. All right. Now it starts to get tricky. What should I do in the center? I should go left. All right. Now, if gamma is 1, what should I do over here at D? I should go left, because what sequence of rewards will I get? I'll get 0, 0, 0. Okay, and then at the end, it's been pushed farther out. I'll eventually get that 10, but that's fine because I'm not actually discounting it. However, if gamma is 1, I'll give you the easy one. I should go here. I'll give you another easy one in the center. It's going to be the same amount of time either way. But here's the interesting case. What happens here if it's 0.1? Well, if I go this way, what am I going to get? I'm not going to get 1. because it's going to be pushed out as time step. If I go this way, I'll get 0.1. What if I go this way? I'm pushed out 1, 2, 3 time steps. So I'm going to get 0.001, and that means it's better to just go right. Because I'd rather get that 1. By the time I get to the 10, it'll be so decayed I don't even want it. So in this case, sooner is more important than more. And that trade-off is encapsulated in gamma, which, among other things, specifies in a soft way what's often informally called the horizon of the agent, how far out I'm thinking. Now, in an MDP, you're always thinking all the way out, but in a way that tails off. And the faster that discount tails off, the more greedy you're going to be, the more you'll pursue rewards sooner rather than larger rewards later. Okay. I think we'll just go from there. A couple more things, and then we'll take a break and talk about algorithms for solving these MDPs. All right. So let's say you're that race car, and you can go fast or you can go slow, and if you play your cards right, you're never going to actually overheat, so the game will last forever. You go fast, fast, slow, slow, fast, fast, fast. And what's your total reward going to be? Infinite. If you go slow all the time, what's it going to be? Infinite. If you go fast when you can and then slow when you have to, infinite. And so that's not good. I mean, it's good if you like rewards because they're infinite, but it's a problem for algorithms that are going to be trying to decide between different actions if all the quantities we're deciding between are just infinity. So, how do we handle the possibility that games could go on forever or and make our algorithms difficult? Well, there's basically 3 solutions, and sometimes they're appropriate and sometimes they're not. One solution is to talk about finite horizon, right? In this case, we terminate all our episodes after, say, something like t steps. Life is an example of this. We don't know what t is, but it's not infinity. And so, in this case, you say, okay, car, you've got 100 moves. Go. Do your best. Okay. Having a finite horizon can give rise to non-stationary policies, where the policy, the optimal action, depends on the time left. First thought, that might be weird. Why can the state, you're in some state, why does what you should do depend on how much time is left? And the answer is, you've seen this in like every sports game you've ever seen. It's like some crazy stuff happens at the end right before the timer runs out. With these cars, you might like risk overheating at the last second because who cares, the game's going to end anyway. And so especially as you get close to the end of a finite horizon game, sometimes the policies can change greatly. But that's one way to make things finite. You just declare they end. Okay. Another way to just use discounting. The nice thing about discounting is even though the sequences of rewards can be infinite and their sums can be infinite, their discounted sums usually are not. So if gamma is between 0 and 1 and the rewards themselves are bounded, the sum through some infinite series magic is going to be bounded. Okay? And then the last thing is some games have what's called an absorbing state, which is that you look at it and you say, okay, I can actually see that the games can go on forever, but with probability 1, it's going to stop. So the probability that you keep lucking out and not having the game end tails off to 0, that's good enough in many cases. Okay. All right, we're going to recap, we're going to break, and then I'm going to give you some algorithms. Okay, so to recap, Markov decision processes, they're like non-deterministic search problems. They've got a set of states, just like search, including a start state. They have a set of actions, just like search, except now instead of the action taking you from an S to an S prime, it can take you to multiple S primes, so we have a transition function which tells you for each S prime how likely it is, possibly 0 if it's not going to happen. And for each transition SAS prime, there's a reward that tells you how many points you get on that transition right then, and then a discount which tells you how to add up a sequence in the appropriate way by multiplying in a discount each time. The quantities that we've talked about so far, we've talked about policies, which is a mapping of states to actions, and utilities, which is a sum of discounted rewards across the entire game of the MDP. Okay? We're going to take a quick break, and then we're going to talk about how to solve them, which will lead into reinforcement learning after next lecture. Okay, 2-minute break, quick break, and then we'll start again. Okay. All right, I don't know if that was actually 2 minutes. It felt like 2 minutes. It was about 2 minutes. All right, we're going to talk about solving MDPs. How do you solve an MDP? The way you solve an MDP, the input, this is really important because in reinforcement learning it's going to look so similar and it's going to be so different. The input when you solve an MDP is an MDP. That means somebody tells you, hey, here are the states, here are the actions, here are the transition probabilities, here are the rewards, and then your output is a policy. It is a mapping from each state to the optimal action. Okay? In order to do that, we need to define a whole bunch of quantities that are going to be useful in this computation. They're actually going to be very parallel to things that you computed with Expectimax search, but we're going to have to define them, and then we're going to have to mathematically state how they relate to each other, which will then turn into algorithms for computing them. Okay, so here are some important quantities associated with an MDP. We'll show this for grid world first. Okay, the first is the value of a state, and this is going to turn out to be both the utility of being in that state and acting optimally, and it's also going to correspond to what Expectimax would have produced. So values, they're written V. There's a value for each state. V is a value. V star is the optimal value. That means the value you will achieve on average, because it's going to be an expected value, on average if you act optimally starting from state S. Okay, some states will have higher values than others because some states are better to be in than others. Right? Much better to be right next to the goal than in some right next to the fire pit. Remember, there are also Q states. S is a state. It corresponds to a max node in Expectimax. And it has a value. That value is what you would do if you sort of acted optimally from that point. A Q state corresponds to a chance node. In the same sense that there are good states and bad states, and you just have to compute the value of each particular state. Like you're in this state, you could wish you were in another state, but this state has whatever value it has. Q states have values. You're in this state and you're performing this action. The value of that Q state is the expected utility of starting out having taken action A from state S and acting optimally thereafter. In the same way that there are some states that are good and some states that are bad, there are some Q states that are good and there are some Q states that are bad. Their values have to do with what will happen if from that state and Q state you act optimally in the future. There's then an optimal policy. Pi is a policy, pi star is an optimal policy, pi star of S is the action recommended by this optimal policy from state S, and it'll be something like, in this state, go north. Okay? So let's take a look at these in grid world. All right. So here's grid world. This is a particular setting. To know these particular values, you need to know what was the noise probability, what was the living reward, what was the discount, and so on. But qualitatively here, you can see that if you are in this state, your value is 1. Because you only have one possible future. You take exit, you get +1. If you're in the pit, the value is -1. You only have one future, exit -1. Everywhere else, these values represent optimal play from that point, and then all the possible outcomes have various probabilities. This is an average, it's an expectation. We'll have to figure out how to compute that expectation, but from here, this means that on average, sometimes you'll accidentally slip and fall into the, from this 8.85 includes both going straight into the good exit and exiting. It also includes slipping here, trying to get back, but slipping again, and then, falling into the fire and so on. And these arrows, you can see, the numbers are the sum of discounted rewards, including the living reward and the final reward, under the optimal policy. The optimal policy is shown by the arrows. Okay? So those are the values of the states. And so you look, this state's really good, because you're just going to get a good reward. This state's pretty good, because unless you get really unlucky, you're going to get a good reward pretty soon. This state down here, in the lower left, the one we had sometimes been calling the start state, its value is only about 0.5. Why? Well, sort of by the time you make your way up, some combination of living reward and probability of falling into the pit and discount have whittled away that +1 and averaged in a whole bunch of other possible outcomes, and so your state's value is lower. It is better to be in this state than this state. But the whole point of computing these values is not to notice that this is a bad state, but rather to figure out what is the optimal thing to do if you're there. Okay, so those are values. Every state has a number, and the farther you are from the goal in grid world in general, the worse your value is going to be. What is that? These are the Q values. So each square is a state, and in each square there are 4 actions, north, south, east, and west. So each of these little pie slices represents that action. The top pie slice is the north action. And so, for example, you can see that 0.85 from the state up here corresponds to taking the action east. So the value of the Q state, 3, action east, is 0.85. There are other Q values for that state. In the same way that states can be good states or bad states, and you'd rather, if you can control it, be in the good states, there's good actions and bad actions. And if you can control it, you'd rather take the good actions. And so if you go south here, you're going to end up in a worse state, and then even if you act optimally thereafter, you're not going to get that same 0.85. And so you can see the Q value here is lower than it is for the other actions branching out of that state. Okay? Oh, and it just had a little episode. Okay. So those are the values. The fundamental operation in solving MDPs is to compute the value, and here we mean Expectimax, or expected value of a state. So we need to know the expected utility under optimum actions, and that's going to be an average sum of discounted rewards. Expectimax computed that, but right now we're going to try to find another algorithm, and in order to do that, we're going to write down recursively some properties that hold between these values that will let us formulate an algorithm. So let's write this in blue. The value of a state. So let's talk about the optimal value of some state S. Oops. We're always going to think about this little Expectimax future. How good is it to be at some state S? Well, I don't know, but I can relate it to some other quantities. I can relate it to how good other states and Q states are. So in particular, I could write down that the value of being in state S is just the maximum over all of the actions I can take from that state of the Q value, the optimum Q value of S comma A. That just says that the Expectimax value of this max node is the max over these of the Q values of those Q states. All right, well that doesn't really help because I don't know Q star either. So what is the value, or you can think about it as what would I get if I ran Expectimax from this chance node S comma A? Well, I can write that down too. So I can go change colors for chance node here. The Expectimax value of being in state S and having chosen A, regardless of whether A was in fact a good action, you have to compute this for all of them. Well, I don't know why I got into state S, and I don't know why I took it upon myself to choose A, but I do know what's going to happen next, right? The average outcome I'm going to get is always going to break down into, I'm going to get a reward from state S, from action A. That reward is going to depend on the S prime I land in. Okay? So I get a reward for the transition. Who knows which S prime it is, but I'm going to get a reward. And then, when I land in S prime, that's down here, I'm going to then act optimally. Right? So, what is that? The optimal action from state S prime is going to give me a score of V star S prime in the future. So my score from S comma A is the instantaneous reward R of SAS prime plus the future optimal reward V star of S prime. 2 more things. 1, that future is discounted, so I stick a gamma there. The second thing is I don't know which S prime is going to happen, right? I'm taking A, but I don't know what outcome S prime I'm going to get. I have to average over them. The way I average over them is I have to take an average. I sum them all up, weighted by the transition probabilities, T of SAS prime, and this thing here is the probability of S prime given S comma A. Okay, so here's sort of a system of equations. Here's a system of equations. People often inline these things. So you will usually see these things inlined. When you see them inlined, it says, what is the Expectimax value of a state? Well, it is the instantaneous reward that you will get in the next time step, plus the future reward from the successor state. The future is discounted. I have to average over all of the possible consequences of my action. So I have to sum over the S primes. I have to take the weighted sum of them. And then, of course, A is under my control, so I take whichever action is best. This defines a system of equations that relate V star of states to V stars of other states. And you look at that and you say, how does that help me? Because now I've written something I don't know in terms of something else I don't know. Okay. Moreover, because of that, Max, this is not a linear system of equations, so you can't just invert some matrix or something like that. So we're going to talk about how to solve these equations, but this is the core system of equations. These are called the Bellman equations. These are the core recursive definitions of values and Q-values of states. These are really, really good things to stare at until you are totally, totally sure you get what they're saying, because you will see variations of these over and over and over again. So you can stare at them. I'm going to erase them and replace them with beautiful LaTeX so you can see in your slides. Okay, because no one should have to read my handwriting. All right, so that was a recursive definition of these values in terms of other optimal quantities. I can define the optimal value at a state. Erase that. I can define the optimal value of a state in terms of the optimal values of Q states. I can define the optimal value of Q states in terms of the optimal values of states using these look-ahead equations that relate values of states to values of states one step ahead in time. And again, these are called one-step look-ahead equations or Bellman equations. Okay, let's look at that racing search tree again. So if we look at this, well, I could run Expectimax on this. But when I look at this, I think maybe there's a better algorithm because those same states seem to appear over and over again, and as we know, their optimal values are all interrelated by the system of equations. Okay? So here's the racing, this is the search tree to depth 1. If I continue it forward, right, that tree is going to grow. It's going to grow rapidly. It's going to grow exponentially fast. And if you look at that, you think it can't possibly be right to run Expectimax over this whole giant tree that's growing exponentially fast, but in fact only has 3 states occurring over and over again. It's a tiny little system of equations. There should be a way to more efficiently just directly connect all these quantities and compute them. And that's what we're going to talk about now as an algorithm for this. So, why should we not just run Expectimax? Well, problem 1, we're doing way too much work, right? Among other things, this whole subtree is exactly the same as this whole subtree. So there's at a minimum there's duplicated work, and in fact there's exponentially duplicated work. That's one problem. Second, and so that's the states repeated problem. Second, this tree is actually infinite, so running Expectimax on an infinite tree is sort of a bad idea. And can you fix these problems right now? If I stop this lecture, you could fix all these problems. You could say, all right, well, look, why don't we cache this stuff? Once I compute something, why don't I cache that? Okay. And actually, instead of doing an infinite tree, didn't we talk about how things deep in the tree, if they're discounted, don't matter? I'll just truncate this at depth 100. Well, actually, if you put these ideas together, you will have more or less reinvented the algorithm we're going to talk about now, which is an algorithm called value iteration. But the algorithm we have works the other direction. Rather than starting at the top, doing things recursively, caching as we go, and trying to depth limit as we go, the algorithm we're going to have is going to start at the bottom and work our way upward until we decide that the tree is deep enough. Okay? All right. The key idea we're going to need in order for us to have this algorithm value iteration is an idea of time-limited values. And so what we're going to do is where V star, so V star was a very tricky quantity. It is the value of being in a state and acting optimally. That's very tricky, right? Because that could go on forever. It could be an infinite depth thing. We're going to define something much more tractable, which is V sub k of a state. V sub k is the optimal value of if you start in that state and play optimally. It's the expected value of starting in that state and playing optimally if the game is going to end in k more time steps. Why is this useful? This is really useful, right? Now suddenly that tree is no longer infinite. And this quantity is exactly what a depth k Expectimax would give if you started at S. So we already have an algorithm. And in fact, if we save repeated work, we'll have an even better algorithm in a second. Okay, so we take a look at this tree, and we say, well, looking at this, there's a computation from, say, state blue of what can happen in 2 time steps. This is that tree. And if we run Expectimax over that, it will compute the average rewards I will get if I act optimally. I do the right thing at all the max nodes. And the game ends after 2. So I can just think of this little tree as V2. At the root, it's of depth 2, and it has some value. And if I see this tree occur 100 times, I can just keep plugging that value in. And it represents the value of being in state blue, which was cool, and acting optimally for 2 time steps. So let's take a look about how this looks in grid world. All right, so here is our favorite example of the grid with a good and a bad exit. V0 is very important to understand, and it's also very simple. If I have 0 time steps, what's a time step? It's a reward. 0 means 0 more rewards. What value will I get under optimal play from the good exit? 0. Okay, no time to get a reward. Bad exit, 0. Lower left corner, 0. Everything's 0 because there are 0 more rewards. So my future score from that state is 0. Okay, easy but not helpful. But now I can ask, what about after one, if I allow myself 1 more reward before I end the game? Well, some of these states will no longer have 0 optimal value. Like the upper right, what can I do in 1 time step? Well, there's only one thing I can do in 1 time step, which is call exit, and I get +1. How about the fire pit? What can I do in 1 time step? There's only one choice according to the rules of the game. Take exit and get -1. Anywhere else, what can I do in 1 time step? I can move and get the living reward. If the living reward is 0, these are the values for 1 time step. So this is V sub 1. These are the values achievable under optimal play on average for 1 more time step. Now what if I had 2 time steps? Think about it. Some of these places, like the lower left, there's just nowhere you can get in 2 time steps that's going to give you any reward other than 0, presuming the living reward is 0. But here's V sub 2. So there's 2 interesting things that happened. One, the upper right square here became 0.72. Why? What does that represent? Well, what can happen in 2 time steps? I can move east, succeed, and take the exit and get +1. That has a certain probability. I can also move east, fail, slip, go in the wrong direction, try to move back and run out of time. That's going to have value 0. And so that 0.72 represents a mixture of things where I didn't quite make it to an exit, and the one case where I just barely made it into the exit in time, and that has, when you average all that together, you get 0.72. The more interesting one is the 0 right below it, the one right next to the fire pit. Why is that 0? Because I can exit the game in 2 time steps. I could jump into the pit and get a -1. But that's not optimal play. So under optimal play, I will avoid that. I will go, I will take some other sequence of actions which does not include that, and I can basically guarantee myself an average of 0. Right? I can make sure I don't actually fall in. And then as I look farther into the future, 4, 5, 6, you can see that eventually I'm looking far enough into the future that even from the lower left I can start to see ways of eventually getting to a good reward. Now I can't see all of them because some of the ways of getting to that good reward are going to take more than 6 or more than 7 or more than 8. Time steps because they involve slipping or some other thing that's going to slow me down. But as I do this, and I sort of push this out, eventually this will stop, and looking farther and farther into the future eventually will not contribute much if there's a discount. I want to show you one more thing on this. I'll show that same thing again. I want you to watch not the values because they're just going to kind of like the green will sort of bleed outward. I want you to watch the arrows. So at first they change a lot. But once I get to here, watch the arrows. The numbers are still fine-tuning. But after a certain point, the arrows are done flipping. And this is a common thing, that as I look deeper and deeper, I have these residual rewards that I can keep accumulating forever. It's like computing the limit of a series, right? I keep kind of accumulating, but the actual policies implied by that depth of search will eventually stabilize. And that often happens long before the values themselves do. Okay, so this actually gives us all we need to define the core algorithm here, which we'll define now, and then we will extend and pick up next time. Okay, and that is, I look at this tree of all the possible futures and ways this game can play out, which includes these same repeating units over and over again. And I look at the bottom, And I say, what's down there? What are these little Expectimax fragments? Well, they're all depth 0 trees. They don't have any rewards in them. So I know I can summarize this exponentially large number of leaves with just the terminal values, v0, which we know are all 0. And then if I look above that, there are a bunch of repeated subtrees. These are the v1 trees over and over and over and over again. Okay? So I can summarize that whole stripe across this tree by just the values of each state that I could then reuse and reuse and reuse. And then if I go up v2, v3, and now at the top there's not actually that much tree, but that value at the top is v4 if I consider this tree to truncate after 4 more rewards. Okay? So this is basically how this algorithm is going to flow. I'm going to start with v0, which I know to be 0. And I'm going to go through and I'm going to compute a new vector of values. Each pass through this, I will be computing a vector which correspond to depth-limited Expectimax computations. And each time this vector gets, each new vector that gets produced for k plus 1 will represent having done Expectimax in a larger and larger tree without having to have done it explicitly. Eventually, these vectors will stop changing very much, and this process will terminate. Okay, so value iteration is the algorithm. It's basically like building a big layer cake, where first I decide, what could I accomplish in 0 time steps? Okay, if I know that, what can I accomplish in 1? If I know that, what can I accomplish in 2? And I stop whenever it appears to have converged. All right, so here's value iteration, the algorithm. We're going to go through this now, and we will extend and improve this next time. In value iteration, you start with v0. That is, for each state, you compute your average rewards under optimal play for 0 more time steps. So it's just a vector of zeros. Then you imagine you are given a vector of vk for each state. This only works when the number of states is manageable and can be enumerated. Okay? And so for each, you have vk. You know what happens if you compute k time step search from each state. And now, using that as a building block, we're going to compute a vk plus 1 value for each. And that means the value, the average rewards under optimal play for k plus 1 more time steps. And that's just the same little Expectimax tree fragment. We say, well, if I want to know what I can achieve on average in k plus 1 steps from S, I'm going to say, well, what am I going to do? Well, I'm going to max over the actions available to me, right? I'm at a state, I can choose an action. When that happens, I'm going to be in a Q state SA, but I need to know what S prime is going to happen before I can compute rewards. I don't know which S prime is going to happen, but I know a distribution over them. So I can take an average. So I sum over all of them. I weight each option S prime by its probability. And now, for each outcome S prime, I'm going to get an instantaneous reward, R of SAS prime. And then, well, I'll have K time steps left. How much score will I accumulate over that K time step? Well, it depends where I land. I landed in S. And then I'm going to play optimally, but with fewer time steps. So it's going to be V sub K, because that's all the time that's left, for state S prime where I landed, and I can stick my discount in there. This looks exactly like the Bellman equations that related optimal values to other optimal values, except that wasn't an algorithm. This is an algorithm. It relates VK plus 1 to VK, but I know VK. If I have a vector of VKs, I can then visit each state, compute its VK plus 1 with a one-step look ahead, like a one-ply Expectimax search, using this update. So how expensive is this? Well, I have to visit each S, so I get a factor of S. And then for each S, I'm going to do a little Expectimax. So I'm going to get a factor of A as I consider each action. And then for each action, I need to consider every possible state that results. In the worst case, every state can result in every other state. So I'll get another factor of S. In practice, you don't usually get that second factor of S because actions have a limited amount of possible successors S prime. Okay? But there's your complexity. Is that good? It really, really depends on how many states you have. So for now, we're going to imagine our sets of states as small, which is exactly the opposite of what we did when we had search. We imagined our set of states was so huge you could never enumerate it. We will fix the dissonance between these two things when we get to a state function approximation about a week from today. Okay, so this thing will converge towards optimal values, but I'll prove that next time. So Should we do an example now? You guys are all like closing your books, so who wants an example? Let's do it democratically. Who wants to just be free? All right. Sounds like we're going to do a quick example. All right, V0. What's V0 from each state? Remember the car MDP? It's 0. Because in 0 time steps, you can get 0 rewards. All right, V1. You don't even need to know the algorithm. You can just think, what will I accomplish on average if I play for one more time step? What if I'm overheated? 0. No more rewards for you. You're overheated. Reflect on your life choices. All right, what if you're in the cool state? There's only one time left. Go for it. Go fast. You're going to get 2. Sometimes, all the time. Who knows what state you'll end up in, but you always get the same reward. Yep. Excellent question. If you are in the state overheated, no, you don't get a minus 10. You get a minus 10 as you transition into that state. In that state, you can imagine there's like a little, whoa, that's unexpected. Okay. You can imagine there's a little loop here that says 0. Yeah, no, it's a great question. Okay, so if you're in cool, you get 2. If you are in the red warm state, what can you accomplish in one time step? Well, you've only got 2 choices. You're either going to go fast or you're going to go slow. And then you can compute. Well, if I went fast, I would be guaranteed a minus 10. If I went slow, I would be guaranteed a 1. That sounds better, and so that represents optimal play. The other one doesn't hurt you because you're not going to do it. Okay, here's where things get interesting. From overheated, you still have 0. The game's over at that point. So let's say you are in the cool state, and you think, okay, I've got 2 time steps left. I could try to enumerate all of the length 2 futures. Right? There's some number of them. I could try to enumerate them all, but that's not what this algorithm does. This algorithm says, what am I going to do? Well, I'm in this cool state, so I'm at cool, and I've got 2 choices. I can go slow or I can go fast. What happens if from cool I go slow? Well, from cool I go slow. If I go slow, I will receive 1 in the next time step. I will be guaranteed to land at cool, and then I will do the optimal thing, V1. I don't have to think about it. Once I only have 1 time step left, I've got a cache right here, lower on the slide. And so what's that? I'll get 2 in the next time step. Or I could go fast. If I go fast, what's going to happen? Well, remember, I'm in cool right now. When I go fast, I am going to get 2 points for going fast. But what happens next depends on whether or not I heat up. If I heat up, which happens half the time, I will land in warm and thereafter receive 1. If I don't heat up, I will land in cool and thereafter receive 2, looking at my cache. And so I'm either going to get 2 plus 2 or I'm going to get 2 plus 1, both equally likely. And therefore, on average, my score here will be 3.5 under optimal play. Okay? I don't have to worry about what happens if I go slow, because I'm not going to do that. I can control that. But I do need to worry that when I go fast, I might heat up or I might not. And that's going to recurse into what I've already computed. And then if you look at this value here, you'll undergo the same computation. You look at it and you say, well, I'm either going to go fast or I'm going to go slow. And in each case, you do the next ply of the Expectimax. It grounds out in V1 that you've already computed, and you can try it on your own. You'll get 2.5. Okay, now if I keep doing this, what are they going to converge to? They will not converge. This is without a discount, this is one of these defective cases where your rewards will go infinite. We'll talk about what that means next time. So the answers are on the slide. Next time I'll talk about why this converges, and we'll talk about another class of algorithms. All right, thanks everyone.